I mean, it's mainly theoretical, although we have now got photographs of them. So we have 2 photographs, which are radio telescope photographs.
Right.
One of the one in the centre of our galaxy, which is a little one. It's called Sagittarius A star. It's a little supermassive black hole. So it's about 6 million times the mass of the sun, which makes it a little supermassive. And then there's another one, the first photo that was taken. It's a collaboration called Event Horizon. And they took a photo of one in the galaxy M87, 55 million light years away. That thing is around 6 billion times the mass of the sun. I mean, imagine that, 6,000 million times more massive than our sun.
Is that the largest black hole we've ever discovered?
No, there are bigger ones than that, but that's that's the scale of them. It's a big-ish one, that. But if you think about it, I mean, so there's a number. It's called the Schwarzschild radius of the thing. So if you took our sun, which you can fit 1 million Earths inside, and collapsed it down to make a black hole, it would form a black hole when it shrunk within a radius of 3 kilometres, about 2 miles. So you've got to take this thing, which is what I have to convert from kilometres to miles, don't I? But it's about...
That's okay, just say kilometres.
700,000 kilometres, so it's about 500,000 miles radius or something like that, the sun. So you squash it down till it's about 2 miles, and then that would form a black hole.
Wow.
The 6 billion times the mass of the sun means you multiply that by 6 billion. So these things, the so-called Schwarzschild radius is, I don't know, larger than our solar system, basically.
Oh
this
my
thing
God.
That sits in a galaxy. So we've got these 2 photographs.
Larger than our solar system.
Yeah, the event. Right. So it's a big structure.
Oh.
That's a Chandra X-ray image of there. That's the M87 black hole. So what you're seeing there is the emission from the material that's swirling around it. It's called the accretion disk. So you have material that's orbiting very fast, emitting a lot of radiation, and that's what you see. It's a flat disk, by the way. So you think Saturn's rings. So this material is very flat. But what you're seeing in that photograph is the light rays being bent around the black hole from that flat disk. So that was a prediction from Einstein's theory, basically. He published it in 1915. And you can predict that that's what one should look like. And then just about, what was that, 4 years ago now, maybe 5 years ago, for the first time in history, we get an image of one, and it looks like the prediction. So It's a remarkable thing.
How phenomenal is that?
Yeah. So we've had those 2 photographs. The other thing we've had is so-called gravitational wave detections. So these are colliding black holes, and they collide and merge together. And obviously that's quite a violent event in the universe. And so that event, that process ripples space-time. So it sends ripples out in the fabric of the universe, space and time. So you get a time storm. So really, we're to think, as we speak now, there will be these very tiny ripples from violent cosmic events passing through this room, and they're changing the rate that time passes, so that as they go through. And we can detect that now. So we have detectors that can pick that up. And so we've seen those collisions as well.
So these collisions, how far away?
Oh, millions of light years away.
And they're affecting what's happening in this room right now?
Yeah, to a tiny extent. So there's an experiment called LIGO, which is the... what it stands for, something like gravitational interferometer. I can't remember exactly what but so basically it's laser beams, and there's one in Washington State, north of Seattle, and one in Louisiana, and they're kind of laser beams, 4 kilometer long laser beams at right angles, and they can detect these very tiny shifts in the, effectively you could say, the length of the laser beam. It's a bit more fiddly and complicated, but it essentially measures the distortion in space-time caused by these ripples. And it's way less than the diameter of an atomic nucleus, by the way, way less. These little sort of, and so we've observed many of those collisions. There it is. There's LIGO. So it's just basically 2 laser beams, but with these ultra high precision thing. And so we've got data now of the collision of black holes and those event horizon pictures with radio telescopes. Black holes are interesting because, going back to the work of Stephen Hawking in the 1970s, it turns out that they demand that we think about both quantum theory and general relativity together. And the quest to unify those two great pillars of 20th and 21st century physics into what's often referred to as a quantum theory of gravity is in some sense a holy grail for theoretical physicists. But the problem has always been, well, is there anywhere in nature that we can look to observe something that requires us to merge those two theories together? And black holes really are the unique place, as far as we can tell, in nature, where we can see a thing just sitting there in the sky that demands that we consider those two theories working together to hopefully reveal a deeper theory. In a sense, it was what's wrong with Stephen Hawking's calculation, which is a weird thing to say sometimes because people think Stephen Hawking surely didn't get his math wrong. But he did actually in his calculation. So what he calculated back in 1973, 1974 is that a black hole, so we picture this thing from which nothing can escape, even light. So when you go in, you're gone, basically. What he calculated is that even though these things are just a distortion in space and time, that's the description of them. So it's almost as if there's nothing there apart from a distortion in space and time. He calculated that they glow, so they have a temperature, so they emit radiation. It's called Hawking radiation. And so important was that discovery. If you go to Westminster Abbey in London, look on the floor of the Abbey on his memorial stone, and he's in there next to Newton. So he discovers these things glow, and he calculates how they glow. A very low temperature, but they emit things, which means that they shrink because they're emitting stuff, and so they're shrinking. So that means they have a lifetime. So first of all, one day they'll be gone. So that means that you have to address this question of what happened to all the stuff that fell in. And his calculation said that there's no record at all of anything that fell in all this radiation that's come off the black hole. So it's purely information-less radiation. So what that means is that black holes destroy information, according to that calculation. And that's a big deal because nowhere else in all of physics does anything erase information from the universe. So it's really true that if I got this notepad and pen, right, and I wrote some things on it, and then I set fire to this, even just incinerated it, put it in a nuclear explosion, whatever. In principle, according to all the laws of nature that we know, if you collected everything that came off, all the radiation, all the bits of ashes and things, and you could just measure it all, then just in principle, the idea is you could reconstruct the information. So it all gets scrambled up and thrown out into, and so in practice you can't do it, but in principle, the laws of nature say that information is not destroyed, it's just scrambled up in a way that you can't reconstruct, right? But this calculation that Stephen did said there is no information in that radiation at all. Zero, just nothing. So it seemed that uniquely in the universe, black holes erase information.
When you say there's no information, like how are you measuring whether or not there's information in it?
So really in bits. I mean, the idea is, and I should say it's very much in principle this, so no one thinks in practice you could reconstruct what I wrote down on this if you set fire to it. But in principle...
Well, maybe sometime in the future, maybe a million years from now.
In principle, you could just collect everything.
Well,
then somewhere in that all that radiation and ashes and light that's come off the thing is the information. It's there. So you could reconstruct the book or what I wrote on this page in principle. But the thing about Stephen's calculation was that even in principle, it said there is no information. And by the way, it's kind of easy to see why, actually, because this radiation, this Hawking radiation that comes off the black hole, it's coming from the horizon of the black hole. So I should say what the horizon is, maybe. So it's if you remember, I said that the sun, if you squashed it down within 3 kilometers of radius, you'd get this kind of distortion in space and time, from which, if you went in across this region 3 kilometers, you went inside it, you couldn't get out. So that's called the event horizon. So you wouldn't notice if you fell through the horizon of the black hole in the Milky Way galaxy. If you went into that one, we could be falling through that horizon now in this room, and we wouldn't notice anything, except that we couldn't get out again. And ultimately, in a few hours, in that case, time would end for us. So you go to the end of time. Not for the big black holes. So these supermassive black holes, we could fall across this horizon. It's just like being in empty space for us. So we would just be talking now, and we could have been talking on the outside of the horizon, and by the time I finished the sentence, we could be on the inside of the horizon, inside the black hole. And according to Einstein's theory, at least, which is the theory that predicted them initially, we could just do that. We could just go in, and we wouldn't notice for a bit. The thing we would notice ultimately is you go inexorably, nothing you can do, you go to this thing called the singularity once you've crossed the horizon, and you are going to that thing. And then the question arises, what is that thing? And one answer is we don't know, but in Einstein's theory it's the end of time. So one way of picturing what's happened here is so distorted is space and time by the collapse of a star or the collapse of loads of stuff to make these big supermassive black holes. We don't quite know how they form actually, but it's collapsing stuff. So it distorts space and time so much that in a real sense they kind of flip over, they get mixed up. And so this singularity, which you might have thought of as the point to which this thing collapsed, this infinitely dense point you might think, but actually more correctly to be seen as the end of time, because everything's got mixed up. So you go to the end of time, and it's just like saying, why can't I escape that thing? It's like, why can't we escape tomorrow? Could black holes be the key to a quantum theory of gravity, a deeper theory of how reality, of how space and time works? Well, I think so. It's interesting. These objects, which have been known, I would say, for 40 or 50 years, but theoretically for the best part of a century, have always been fascinating. They're odd things. The simplest way to describe a black hole would be a region of space from which even light can't escape. Predictions that such objects existed go all the way back to the beginnings of relativity, back at the turn of the 20th century. But actually, really, I would say into the 1960s, perhaps even into the 1980s, many physicists felt that because of the intellectual challenges that these predicted objects pose, many physicists felt that maybe nature would not create them. I even saw the great physicist Steven Weinberg say that he, in some sense, hopes that these things would not exist because they're so confusing. But we now know that they do exist, and so we have to face the challenges that they pose. What would happen if Earth or a human fell into a black hole? It depends on the mass of the black hole is the technical answer. So if it's a small black hole, by which I mean just a few times the mass of our sun, then you get ripped apart by the tidal gravitational forces before you actually fell in. So as you approach the event horizon of the black hole, it becomes very nasty. But for the very big black holes, so like the one we have a photograph of, we've got two photographs actually. One of the one in the centre of the Milky Way, and one in the centre of a galaxy called M87, which is a very big one. It's something like 6 billion times the mass of the Sun. So a supermassive black hole in M87. It's 55 million light years away, that one. And if you fell towards that one, then as far as we know, you would fall across the horizon into the interior of the black hole, and you'd be unaffected. You wouldn't notice as you fell across the horizon. And then you'd have something like, I can't remember the exact number, but it's something like 30 hours-ish inside the black hole until you approach the singularity, which is in your future when you cross the horizon. So it's not something you can avoid. It's like trying to avoid tomorrow. You can't do that. So you go to this singularity, which is, in Einstein's theory, the end of time. And just before you get there, you get spaghettified, which means you get stretched in one direction and squashed in the other, and even your atoms get ripped apart, and then you go to the end of time. So that's not nice. However, if you put quantum mechanics in, which goes back to Stephen Hawking's work in the 1970s, then we can start debating about what the horizon is, and there are certain ideas that you might get when viewed from the outside. You might look to get, it might appear you get incinerated before you cross the horizon, and all your ashes come back out into space again. But from your perspective, it seems that you wouldn't get incinerated. From your perspective, you'd go inside and then you get spaghettified. And then the question is, do you get vaporized or spaghettified? And the answer might be both, which is called black hole complementarity, which is all very complicated. So it's one of those things. Again, ultimately, the answer to what would happen if Earth or a human fell into a black hole is, for a big black hole, we don't really know. But for a small black hole, you would get ripped to bits before you fell across the horizon. Yeah, so these little ones were little, you know, they're a few times the mass of the sun, and they're from collapsed stars. So they are stars at the end of their life, very bigger than the sun, more massive than the sun, but they run out of their fuel and they start to collapse because gravity squashes them. And if they're sufficiently massive, then there's nothing that can stop the collapse. And so they collapse, as far as we know, to a point. Right, essentially an infinitely dense point. We don't really know what happens we don't know what happens right in the middle. But they collapse to such an extent that there's a region around it from which light can't escape. And so nothing can escape. And that's a black hole. They're still there. They're surrounded, this region where if you fall in, it's called the event horizon. And if you go across that horizon, then you are going to the center. There's one way of thinking about it, which is quite cool, which is that the time and space sort of flip is one way to think about it. So in the same way that we are going into the future now, so we're going to tomorrow. There's nothing we can do about it. We are going to tomorrow. In the same way, if you fall in across the event horizon of a black hole, you are going to the middle, the singularity it's called. So that's your future. Every line of your future points to the center of the black hole. So it's kind of the ultimate of no escape, the ultimate prison. You're going to get squashed to an infinitely dense. No, because if something like the sun,
we have a small star.
It's quite small, yeah. And when it collapses, there's a sort of a pressure, a force, if you like, which is caused by the fact that electrons don't like to be very close to each other. So it's called the Pauli exclusion principle. But essentially what happens is that, so as they get squashed closer and closer together, they move faster and faster to sort of get out of each other's way, if you like. And that makes a force which holds them up. And so that creates what's called a white dwarf star. So you can have a blob of matter. They're about the size of the Earth, but they're about the mass of the sun. And so that's for smaller stars. They end up as these white dwarf things, which are very dense objects. There's another version, which is called a neutron star, which is the same thing, but for neutrons. And they move faster and faster. So if it's massive enough that it overwhelms the electron thing, then the electrons sort of crush into protons and turn into neutrons, and the whole thing starts again. And so a neutron star can be, you know, at least 1.5 times the mass of the sun, let's say, but it can be about, 10 miles across? So that's an incredibly dense ball of matter held up by the neutrons moving around. It's got a fancy name. It's called neutron degeneracy pressure, but that's what it is. But if you go even bigger, then even that can't hold it up. And as far as we know then, there's no known force that we know of that can hold the thing up if it's too massive. And so that's when it just almost winks out of existence, if you like. It collapses and collapses and collapses. And that's when you get a black hole. So the answer is the energy comes out. It's in the Hawking radiation, right, ultimately. But the kind of deeper question is what happens to the information, which we're beginning to touch on now. So we've said a few things here. We've said if you throw this book into the black hole, then from the perspective of the book, if it can have a perspective, it goes in, it sails through the horizon and gets spaghettified and essentially meets the end of time, scrambled up in a big mess, right? From the point of view of someone outside, it gets incinerated, right? And essentially radiated out again, somehow in the Hawking radiation. So we've got two pictures.
Yeah.
One picture is telling us, as you said, then the black hole evaporates away. So if you're thinking of this as going in, then it's erased from the universe, according to Stephen Hawking's original calculation. Is because there's a very precise problem posed. So it's not some kind of thing like trying to understand a singularity or understand the Big Bang, or where you can just say, well, we're miles away from understanding. The challenges were posed in a region of space, the vicinity of the event horizon, where we thought we had control of the physics. And so that's really useful, because it means that it should be the case that calculations can be performed to resolve. The reason this challenge, this apparent contradiction, this fundamental problem, garnered so much attention is because it occurred, the problem came from physics that everybody thought they understood. So calculating in a region of space under conditions in the universe where we thought and assumed that we had full control of the mathematics of the theories. That's really interesting, because it sort of means you have a chance catching a glimpse of some kind of deeper theory by resolving this contradiction. So that's why more and more people got interested in the black hole information paradox. It turns out, if we fast forward to the present day, and a series of papers are still being written, so this is still research that's happening as we speak. But it turns out now that the general view, I would say the generally accepted view, is that black holes do not erase information from the universe. So in principle, if you could collect all that Hawking radiation emitted over eons, right? The lifetimes of some of these black holes, by the way, 10 to the power 120 years plus for some of the big ones. It's one with 120 noughts after it. I mean, the universe is only one with 10 noughts after it years old at the moment, 10 billion years old or so. So we're talking about timescales vastly longer than the current age of the universe. But when they've gone, then in principle, we now think you could collect all that radiation, in principle, put it into some quantum computer, carry out some operations on all that radiation, and reconstruct the information about everything that fell in. But the implications of that, the mechanism by which that happens, I would say it's profoundly exciting, because it really does seem to be giving us a glimpse of a deeper theory of gravity. The simple way to say it, it seems that space and time are not fundamental. So one view, and I emphasize that there are other views, we're at the cutting edge of research now, but one view is a field which has become known as emergent space-time. So what does that mean? It means that space and time themselves are not fundamental. In Einstein's picture, we assume there is such a thing as space-time. This four-dimensional surface, manifold is the technical term, but you assume it. It's part of the model. There are such things as space and time woven together into the fabric of the universe. What they are, Einstein has nothing to say. It seems that there is a deeper theory underlying what we think of as space and time, which is a quantum theory. And so the idea is that space and time themselves emerge from what? From quantum entanglement, from some kind of smaller parts or pieces. We don't know what those things are. We don't know the nature of them. But it does seem that there's a deeper underlying theory from which space and time emerge. That is what we call the quantum theory of gravity. But the key thing to understand is we've been driven to that picture by asking very clearly defined, precise questions about how black holes behave, which goes all the way back to Einstein, and then to Stephen Hawking and many others' calculations through the 70s and 80s. Well, supermassive black holes are fascinating things. So these are the black holes that we have images of radio telescope images. We have two images from a collaboration called the Event Horizon Collaboration. One of a black hole, it was the first one they acquired, of a black hole in a galaxy called M87, which is about 55 million light years away. This is a big galaxy, something like 1 trillion suns. And in the center of that, we've long suspected there was a black hole. Now we have an image of the black hole. It's a black hole that is so supermassive. It's over 6 billion times the mass of our sun. A big black hole by any measure. We also have an image, by the way, of the rather smaller supermassive black hole at the center of the Milky Way galaxy, which is only about just over 4 million times the mass of our sun. So it's a little one, but still big. We think that virtually every galaxy has a supermassive black hole at its heart. Caveat a little bit, because a couple of papers have been released recently suggesting that there may be galaxies observed where there are no supermassive black holes. There are lots of galaxies in the universe. Maybe there are exceptions, but it's fair to say that virtually every galaxy has a black hole at its center. That's an interesting observation because we don't know how those form. One of the reasons is we don't really fully understand how the first galaxies formed in the first place. It's current research, live research. One of the goals of the James Webb Space Telescope is to observe the formation of the first stars and galaxies. It can do that because it can detect very faint, very long wavelength light, which is what you need to detect if you want to look far out into the universe and therefore far back in time towards the origin of the first stars and galaxies. So the JWST new instrument that's looking at that. There are also a series of new radio telescopes being built. The Square Kilometre Array, for example, in Australia and South Africa, which is a radio telescope array aimed at observing the formation of the first stars and galaxies. So this is live research. It's a fundamental question. How does structure form in the early universe? Not only are black holes interesting from a theoretical perspective, allowing us to peer or uncover deep questions or ask deep questions about the structure of space and time itself, but they're also key to understanding how galaxies form and how structures form in the early universe. How many black holes do we know of? So direct observation, in terms of radio telescopes, we have a direct observation of 2 of them from the Event Horizon Collaboration. The one in our galaxy, the Milky Way, and the one in the galaxy M87. We also have what I would call direct observation of black hole collisions. This is a completely different technology, a different approach. It's called gravitational wave astronomy. So gravitational waves are ripples in the fabric of the universe. Let's describe them like that. Although I once heard Kip Thorne call them a storm in time, which I think is also a very beautiful idea. And so the idea is that what is a ripple in space and time? They be passing through everywhere now, so through you and me, through the space in which we sit. And they're ripples in space and time, so time speeds up and slows down a bit as these things go through. Distances kind of shrink and expand a little bit as well. So they're real distortions in space and time. And they're caused by, well, actually, pretty much everything that happens in the universe at some level, but they're very, very faint and difficult to detect. The ripples we've been able to detect come from the collisions of black holes or the collisions of neutron stars. So these are highly energetic events in the universe. And the observatory is called LIGO and Virgo. These are essentially laser beams, so-called laser interferometers, about 2.5 miles actually long, 4 kilometers long, at right angles to each other. And they can detect little shifts in the distance between the mirrors between which the laser beams bounce, far, far smaller than the diameter of the nucleus of an atom. So tiny, tiny ripples in the fabric of the universe. By observing those ripples, we can see the collisions of black holes. We tend to see the collisions of big ones, and that's what's called a selection effect. The big ones are more energetic, and so the gravitational waves are easier to detect. But the collisions we're seeing are between black holes that are For example, around 30 times the mass of our sun. And the number of those collisions is, I think it's fair to say, larger than anyone would have imagined before the observations were made. So it seems there are quite a lot of these black holes floating around that are very massive indeed, 30, 40 times the mass of our sun and upwards. And I think it's fair to say the formation of those things is a mystery as well. It's presumably that they're formed from the collapse of very massive stars, but the number of them, I think it's fair to say, took everybody by surprise.